I'm so excited about this video. I can't even wait to get underway. In this video, we're going to look at what is the motivation behind studying Galois theory the way that we're going to study Galois theory. In other words, what was in Galois' mind when he was developing the way in which he looked at solutions of polynomial equations. And this is a video that personally for me, I had to go over it a number of times before I really sank in what was happening here. So this is a video to watch and to rewatch, and I'm going to try to make it as entertaining as possible for that reason. Because this really provides us with the motivation for why we need algebra that's as abstract as the algebra we're going to look at in order to study a question that's as concrete as the one Galois was trying to answer, which is, when can we solve polynomial equations through a simple process of extracting simple radicals? So we're going to start by reaching for a metaphor in this video, because our interest is in, instead of solving polynomials, figuring out whether a polynomial has roots that are similarly related one to another. In the last video, we looked at an example of a fourth-order polynomial that its roots kind of came in two pairs. It had a plus and minus 4, which were very similar, and it had a plus and minus 4i that were also very similar. And so that observation of similarity should tell us something about the solutions of that polynomial equation. And so the metaphor I'm going to reach for is one of interchange, and it comes from a classic 1970s coffee commercial. Let's just take a look at it real quick.
In New York, known for its fine dining, we're at world-famous Tavern on the Green restaurant. Tonight, we're secretly replacing the fine coffee they normally serve with rich, dark, sparkling Folgers crystals. Let's watch.
It's really an excellent cup of coffee.
Real good.
I like it. It's a rich flavor.
It's Folgers crystals.
Really? Excellent. I'll buy it.
Folgers crystals. Coffee rich enough to be served in America's finest restaurants.
So from a marketing standpoint, what's the point of that commercial, the old classic commercial? The point is that when they exchanged the gourmet coffee for the instant crystals coffee, that the diners didn't notice a difference. Why does that tell us something about their instant coffee? Well, if the diners couldn't tell the difference, then maybe their instant coffee really was pretty gourmet after all, and therefore maybe you should go out and buy some, right? No endorsement implied. So when I trade out one kind of coffee for another kind of coffee, if nobody notices, that means that I have a pair of coffees that are pretty similar one to another. So the objective is going to be to take a polynomial and investigate what happens when I take its roots and I swap them out one for another. If I trade out a 4 for a minus 4 or something, will the polynomial notice? Will other polynomials that are satisfied by those roots notice? Because if no polynomial satisfied by these roots notices when I interchange a pair of those roots, then that probably means that that pair of roots are really similar, especially really similar in view of the number system out of which that polynomial is built. So plus and minus 4, when I swap them out, does anybody notice? Plus minus 4i, if I swap them out, will anybody notice? For example, if my polynomial is built on real coefficients, it might notice if I swap plus minus 4, but it might not notice if I swap plus minus 4i, because those aren't real. So that's going to be the name of the game here, is that if I switch around the order of the roots in my polynomial, will anyone notice? Will any polynomial that those roots used to satisfy in this order now not be satisfied in a different order? That's the question we're going to investigate, starting with a very simple example from a quadratic polynomial. So let's get down to basics. Let's take a quadratic polynomial, t squared minus 7t minus 18. If I can factor it, then I can find what the roots are. And this one happens to be simple enough to factor, t plus 2, t minus 9, and from the zero factor property, I know what the roots are, negative 2 and 9. Let's call those alpha and beta. Then again, how did we just do that? When you have to explain to an algebra student studying algebra how you factor a polynomial, you have to come up with some process of discovery. How did we discover t plus 2 and t minus 9 out of the coefficients of this quadratic polynomial? Well, you've probably jumped ahead of me and noticed that how we factor is that we look for a pair of integers, if it exists, whose sum is equal to negative 7 and whose product is equal to negative 18. Right? And that actually leads us to a theorem about quadratic equations, that if alpha and beta are both roots of a quadratic polynomial t squared plus bt plus c, then if I add those roots together, I get the opposite of b, and if I multiply them together, I get c. This is called the sum and the product of the roots theorem, which actually is stated as a theorem in some high school algebra classes. But it's not too difficult to convince yourself of. Just because this is analogous completely to the process by which we factor quadratic equations. So negative 2 plus 9 are my two roots, and sure enough, if I add them together, I get positive 7, which is the opposite of the coefficient of t in my polynomial. Likewise, if I multiply my two roots, negative 2 times 9, I get negative 18, which is exactly the constant term in my original polynomial. So these two equations, alpha plus beta equals negative b, and alpha times beta equals c, these are equations that will be satisfied by whatever the roots of t squared plus bt plus c are. So in our example, we know, before even we solve this equation, that the roots of this polynomial will satisfy alpha plus beta equals 7, and alpha times beta equals negative 18. That doesn't directly help us to solve this equation, but it does give us some information. So now we get to the question of what happens if I interchange those two roots, because our hunch is that it shouldn't matter whether my first root is negative 2 and my second root is 9, or whether my first root is 9 and my second root is negative 2. Roots don't have a natural kind of ordering to them. So if I swap the order in which I consider my roots to be in, then how much does it really matter? So if I interchange alpha with beta, what happens? Well, in the sum and product of roots theorem, notice interchanging alpha and beta in the first equation, the sum of the roots theorem, and interchanging alpha and beta in the product of the roots theorem, actually gives me two equations that are exactly identical arithmetically to the first two, because addition and multiplication are commutative. So these equations, these two equations, don't notice if we swap alpha with beta. If your gourmet coffee is switched out for your instant coffee crystals, then no one in the restaurant notices the difference. So these two equations can't tell if I swap alpha with beta. But what about other polynomials that have alpha and beta as roots? So if this polynomial alpha plus beta equals 7, which we know is satisfied by the roots of our polynomial p that we're looking at here, if that equation is satisfied by our roots alpha and beta, is it still satisfied when I swap beta with alpha? Sure. So this equation doesn't notice. Likewise with the product doesn't notice because alpha beta equals beta alpha. But there are also other polynomial equations that are satisfied by alpha and beta. For instance, alpha satisfies alpha squared equals 7 alpha plus 18. If I swap alpha with beta in that equation, I get beta squared equals 7 beta plus 18. But if one of these is satisfied, then the other is satisfied, because it turns out both of them are equivalent to being a root of p in the first place. So some polynomial equations in alpha and beta don't care if we swap alpha with beta. If they're true in one ordering, then they're still true in the other. But other polynomial equations definitely do matter. So here's a simple polynomial equation with integer coefficients that has alpha equals negative 2 and beta equals 9 as a solution. You can check that. Just put in a negative 2 for alpha and 9 for beta, and sure enough, 9 alpha plus 2 beta is indeed equal to 0. But what happens with this equation when I trade alpha with beta? And I get 9 beta plus 2 alpha equals 0. Well, it doesn't take a whiz to put in negative 2 and 9 for alpha and beta and see that this equation is not satisfied. So this polynomial equation cares if we trade alpha with beta. Right? Alpha and beta are still the roots of p, but if I put them in one order, it satisfies this equation. If I put them in the other order, it doesn't. So these two equations are not equivalent one to another. We can come up with fancier examples too. Alpha to the fourth minus alpha beta is equal to 34. Check that alpha equals negative 2, beta equals 9 satisfies this equation. Sure enough, that works out. But if I swap alpha with beta and get beta to the fourth minus beta alpha equals 34, now disaster. If I put in negative 2 for alpha and 9 for beta, left-hand side is 747, not 34. So the equations listed here on the right care which order you put alpha and beta into them, whereas the equations on the left don't. So when we trade out the gourmet coffee for the instant coffee crystals, half the dining room notices and cares, and the other half doesn't. So we can sort of please half the diners, but maybe not the other half. And it may not necessarily be half and half. There may be a whole lot of polynomials, in fact, that do care when I trade this alpha with this beta. And that process of caring somehow tells us something about these two roots. It tells us that the roots of this polynomial equation aren't very similar. Right? That the instant coffee really is not a great substitute for the gourmet coffee. That when I trade out alpha with beta, something changes, something fundamental changes, because those numbers are not similar enough in view of the coefficients of this original polynomial. So what happens if the shoe is on the other foot? Is it possible to fool the entire dining room as they do in the instant coffee commercial? Well, here's another polynomial, p of t equals t squared plus 4. Its roots, as we can quickly show, is alpha equals square root of negative 4, and beta is minus the square root of negative 4. So, looking at the sum and product of the roots theorem, that means that the sum of these roots has to be 0, because that's the coefficient of the t term, and the product has to be equal to 4. And these two equations, of course, are satisfied in whichever order we put alpha and beta, right? Trading alpha and beta will always give us an equivalent set of equations for the sum and the product of the roots theorem. So when we trade out the gourmet coffee for the instant coffee, these two equations never notice. These are the least fussy diners in the dining room, right? You can pull it over on them every time. They have no taste for coffee. Mathematically, we call these equations fully symmetric. In other words, any order in which I switch out alpha and beta is going to lead to an equivalent equation. But of course, there are going to be fussy diners in general. So here's a diner that looks like it might be very fussy. So this equation doesn't look like it ought to be symmetric with respect to an interchange of alpha and beta. Alpha to the fourth beta minus 16 beta equals 0. Check this one out. Sure enough, if I put alpha and beta as listed into this equation, we do get this equation to be satisfied. But this looks like a really fussy equation. Will this coffee snob notice if I trade out its instant coffee for its gourmet coffee for instant coffee? So let's swap alpha with beta and see what happens. So I get beta to the fourth alpha minus 16 alpha equals 0. If I put, again, my same alpha and beta into this equation, it turns out that it's still satisfied. So this equation, even though it looks really fussy, doesn't notice when we trade out alpha with beta. So that tells us something about this polynomial. It tells us that the roots of this polynomial are so similar with respect to the way that this polynomial is built that no other polynomial that they satisfy will notice over the integers or over the real numbers when we swap alpha with beta. Maybe the reason is that these two roots happen to be non-real numbers,